Okay, we're going to continue the next video for the DC motor analysis example 2. In this example 2, we are going to calculate the motor speed at a certain current condition. If you haven't watched the first video, please watch the DC motor analysis example 1, then continue to watch this video. Now we're going to move to a second example. Again, this is a DC motor with no armature reaction. This time we're going to calculate the speed of the motor when there's a certain current condition set in the motor. So we have the same motor from example 1. It's a separately excited DC motor. It has compensating windings, that's why there's no armature reaction. From example 1, we had a terminal voltage of 150 volts, an armature resistance of 0.2 ohms, a field winding of 1800 turns, field winding resistance of 100 ohms, and a field winding voltage of 180 volts. Now we have this adjustable resistor and it is set at 200 ohms. So what we're going to do, we're going to calculate the speed of the DC motor when the line current is 90 amperes. So the line current is this IL. Okay, so the question is when IL is 90 amperes, R adjustable is 200 ohms. What is the speed? What is the speed? So what we first need to do, at an R adjustable of 200 ohms, we're going to calculate the field current. Okay, so as we know, field current is VF over RF plus R adjustable, which is 180. RF is 100 ohms, R adjustable is 200 ohms, so that gives us 0.6 amperes. Now, we're also set at a line current of 90 amperes, so that means your IL is 90 amperes. From our separately excited machine, we can get the armature current. The armature current IA is equal to IL. Why? Because this is a separately excited DC machine. Okay, that is the difference between separately excited and shunts. So when IA equals to IL, therefore IA is equal to 90 amperes as well. Then we're going to do KVL at the armature circuit. So KVL of the armature circuit the purpose is to find EA. So EA is equal to VT minus RA IA. And VT is 150 volts, RA is 0.2, and IA is 90 amperes. So this gives us an EA of 132 volts. So this is the induced voltage when the armature current is 90 amperes. And we know that EA is equal to K flux omega. So therefore, to calculate the speed, we need EA divided by K flux, which is 132 divided by K flux. And we're going to call this equation 1. So we can't solve the speed yet because we don't know the value of K flux. So to find K flux, we need to use the table. So using the table, which is given in the question, we need to see what is the value of the EA at the field current. So we know that IF is equal to 0.6 ampere. We just calculated that. And from the table, when IF is equal to 0.6 ampere, the EA0 is 102 volts at a speed n0 of 1500 rpm, which is the speed of the table. Now omega 0 is n0 times 2 pi over 60, which is 1500 times 2 pi over 60. Unit is radians per second. And we know that EA0 is equal to K flux omega 0. So substituting EA0, 102, K flux omega 0 is 1500 times 2 pi over 60. So from the table we can get K flux 102 over 1500 times 2 pi over 60, which is 0.649, and we're going to call this equation 2. So what we've learned so far, or what we've calculated, when R adjustable is equal to 200 ohms, the IF was 0.6 ampere, and from the table we got K flux is EA0 over omega 0. From the table we got EA0 of 102 volts at N0 of 1500 rpm. So we need to change this 1500 into radians per second, and we got a K flux of 0.649, which is equation 2. And then at a line current of 90 amperes, we said that the separately excited would have IA equal to IL, which is 90 amperes, and we got the EA 132 volts. This was from the KVL of the armature circuit. So the speed at IL of 90 amperes is EA divided by K flux, which is 132 divided by K flux, and we had called this equation 1. So now we need to substitute K flux into equation 1. So we're going to substitute equation 2 into 1 to find the speed. So EA over K flux 132 over 0.649 gives us a speed of 203.39 radians per second. So this is the speed of the DC motor when IL is 90 amperes. Now, let us look back from what we had in example 1 and example 2. Example 1 was the same machine, but we calculated the no-load speed. At no load, IA is equal to 0, EA is equal to VT, which is 150 volts, and we got a speed of, no load speed of 231.12 radians per second. This was no load speed at R adjustable equal to 200 ohms. In example 2, we had the same R adjustable of 200 ohms, but the IL was 90 amperes, which is equal to IA, and we got a speed of 203.39 radians per second. So if we were to plot the speed of the motor in radians per second against the torque, which is proportional to IA, this point here, the induced torque is 0 because IA is 0, and the speed is actually no load speed, which is 231.12 radians per second. Now, with the same adjustable resistance, that means the field current is the same for both example 1 and example 2. When the IA increased to 90 amperes, the induced torque is not equal to 0 because IA is 90 amperes. So later I'll show you how to calculate the torque. We find that the speed was 203.39, which is lower than the no load speed. So if we were to plot this on a graph, it is straight line. Let me draw that better. So connecting these 2 points, we find that as IA increases, the speed will reduce. And this graph is what we call the terminal characteristic of the DC motor, where the no load speed is always much bigger than the speed when the torque is not 0. So when you do your calculations, if you find the speed at a certain armature current, it should be less or lower than the no load speed.